Implicit differentiation. Let's consider the following example. If x squared plus y squared equals 25, find dy dx. Then find an equation of the tangent to the circle at the point 3, 4. So let's just notice in the graph over here, we have x squared plus y squared equals 25, which is a circle with radius 5. And the point 3, 4 is a point on the circle right about here. And we are looking for the equation of the tangent line to that point. Now, one way we can do this is we can take the equation x squared plus y squared equals 25, and we can solve for y. To solve for y, we would subtract x squared from both sides, and this would give us y squared equals 25 minus x squared. And then we can take the square root of both sides, and this is going to give us y equals plus or minus the square root of 25 minus x squared. Now, one problem with this is not a function, because a function can only give you a single value when you plug in a value of x. And this gives us two values because we have plus or minus. So what's happening here is there are two functions here. We have positive square root of 25 minus x squared, and we have negative square root of 25 minus x squared. And just for clarity, the positive half of the function represents the half of the circle that is above the x-axis. And the negative half of this function represents the half of the circle that is below the x-axis. So if we're looking for the equation of the tangent line at the point 3, 4, we are looking at the top half of the circle, which means we are interested in this function. So now from here, what we could do is go ahead and take the derivative. So let's go ahead and rewrite this as 25 minus x squared to the 1/2 power, and dy dx would be 1/2 25 minus x squared to the negative 1/2 multiplied by the derivative of the inside function, which is negative 2x. And if we simplify this, we can express this as negative x over 25 minus x squared to the positive 1/2. So I'm just canceling the 2's here and then moving the power down to make it a positive power, and we could finally express this as negative x over the square root of 25 minus x squared. Now, to find the equation of the tangent line, we need the slope, and the slope is going to be the derivative evaluated when x is equal to 3, because the point of tangency here has an x coordinate of 3. And so this would be negative 3 divided by the square root of 25 minus 3 squared. And this is negative 3 divided by the square root of 16, which is negative 3/4. And then from there, we can find the equation of the tangent line by using this slope and plugging the point and the slope into the equation of a line. And when you multiply all this out, you will get y equals negative 3/4 x plus 25 over 4. And this is the equation of the tangent line. And there is nothing wrong with this method, but I want to show you a different method, because what happened in the beginning is you had a function x squared plus y squared equals 25 that was implicitly defined. What that means is that y was not by itself. Y was mixed in as a part of the x's. We did not have it solved for y in the beginning. Now, it is true that in this case, we were able to solve for y Remember, that gave us two solutions, and then we were able to pick the one that we needed to look at in order to find the slope of the tangent line. But this will not always be the case. Sometimes you will not be able to solve for y, and you will need another method for finding the derivative. So we're going to talk about this method, which is called implicit differentiation. To do this problem using the process of implicit differentiation, I'm going to start with my equation x squared plus y squared is equal to 25. And I want to think of y as being some unknown function of x. And so if I write it in this way, we would have x squared plus y, which could be replaced with f of x squared is equal to 25. And then what I'm going to do is simply take the derivative of the left-hand side of this equation, and that should be equal to the derivative of the right-hand side of this equation. And when we do this, we are just going to take the derivative of x squared plus the derivative of f of x squared, and that will equal the derivative of 25. Now we know the derivative of x squared is 2x. Now what is the derivative of f of x squared? Well, if we use the chain rule, we know it's going to be 2 times f of x to the first power multiplied by the derivative of the inside function, which is f prime of x. And this will be equal to the derivative of 25, which is 0. And now to find the slope of the tangent line, I need to solve for f prime of x. So let's get rid of this first power there. I'm going to subtract 2x from both sides. And this will give us 2 f of x times f prime of x is equal to negative 2x. And then to get f prime of x all by itself, I'll divide both sides by 2f of x. The 2's cancel here, the f of x cancels here, and we get f prime of x is equal to negative x over f of x. So I'm just canceling these 2's here. And then I just want to remind you that this would be the same as f prime of x is equal to negative x over y, because y is f of x. And so now we have a derivative of this function that is completely different, at least in terms of how it looks, from the derivative we found a few minutes ago. The next step would be to find the slope of the tangent line. And the slope of the tangent line is the derivative negative x over y evaluated at the point 3, 4. So we're going to plug in x equals 3 and y equals 4, and you'll notice that you get the same slope, negative 3/4. And then from there, the equation of the tangent line would be found in the same way. And I won't finish this because we already did this a few minutes ago. So this is the process called implicit differentiation. Notice that basically what I did is I just took the derivative of both sides of the equation as it was. The only thing I did to help us understand what it was that we were doing is I replaced y with f of x to help us see the derivative of this as a chain rule. Now, you don't actually have to take this step, so let's go through this one more time, but this time I'm not going to make the substitution y equals f of x. So to take the derivative here, I'm going to start by simply taking the derivative with respect to x of the left-hand side of the equation and the derivative with respect to x of the right-hand side of the equation. And then, of course, we will take the derivative of x squared plus the derivative of y squared, and that will equal the derivative of 25. Now, Now the derivative of x squared, we know that is 2x plus, and this is the tricky part, the derivative of y squared is 2y, but because y is a function of x, we have to multiply by the derivative of y with respect to x, which is dy dx. And this is equal to the derivative of 25, which we know is 0. So the key point is when you're using the chain rule, anytime you take the derivative involving a function y, you must follow it up with a dy dx. And I just want to talk very briefly about this a little bit more to make sure that you understand it. So what we're doing here is we're applying the chain rule. The derivative of y squared is 2 times y to the 1, and then we're multiplying by the derivative of your inside function. So you can kind of think of it as like 2 times y to the 1, and then the derivative of the inside is dy dx. Once you do that, then from there it's just a matter of subtracting 2x from both sides, and this gives us 2y dy dx is equal to negative 2x. And then finally, I'm just going to divide both sides by 2y. And when I do that, these cancel out, and I get dy dx is equal to negative x over y. And that's the same thing we got just a few minutes ago. But you'll notice that the amount of work that we show here is a little bit less because we're not expressing y as f of x. And then, of course, the slope we would find by taking that derivative and evaluating it at the point 3/4, and of course, this gives us negative 3/4. So let's take a look at some other examples. In the second example, we want to find y prime given the equation x cubed plus y cubed equals 6xy. And then we want to find the tangent to that curve at the point 3, 3. So let's focus on the derivative. We have x cubed plus y cubed is equal to 6xy. To use implicit differentiation, we are just going to take the derivative with respect to x of the left side and the derivative with respect to x of the right side. Now this becomes the derivative with respect to x of x cubed plus the derivative with respect to x of y cubed equals, and then here I'm going to pull the 6 out because it's a constant, and then I have the derivative with respect to x of x times y. So this is a normal power rule derivative. This right here is a product rule derivative. And this, of course, is a normal derivative, but we are taking the derivative of a y term, so we need to make sure we have a dy dx. And of course, we will get a dy dx on the other side as well. So let's go through this. The derivative of x cubed with respect to x is 3x squared. The derivative of y cubed with respect to x is 3y squared times dy dx. On the right-hand side, we have 6 multiplied by, and now the derivative of xy is a product rule. So we are going to take the first function x, multiply it by the derivative of the second function. So the derivative of the second function y is simply dy dx, right? Because it is the derivative of y with respect to x. Plus, then we're going to take the derivative of the first function, which is 1, multiplied by the second function. So again, this is just the product rule. Now, if we clean this up, we get the following. And all I did here was distribute the 6 to both of these. And now, remember what you're trying to do. You're trying to find the derivative dy dx. So we've got a term here with dy dx. We have a term here with dy dx. We need those terms on the same side of the equation. So I am going to subtract this term over here, and I'm going to subtract this term to the right side. So on the left-hand side, we have 3y squared dy dx minus 6x dy dx. And on the right-hand side, we have 6y and the 3x squared. We're going to subtract that over to the other side. So that becomes minus 3x squared. Now the next step is to notice that you have a common factor here, and we can factor that out. So we have dy dx multiplied by 3y squared minus 6x is equal to 6y minus 3x squared. And the final step here to solve for dy dx would be to divide by 3y squared minus 6x. That will cancel this, and we end up with dy dx is equal to 6y minus 3x squared divided by 3y squared minus 6x. Now that answer is correct, but you can actually factor a 3 out of the numerator and also a 3 out of the denominator. And once you do that, you can cancel out that common factor, and the simplified form of our dy dx is the following. The important thing to keep in mind here is that when you take a derivative of y, you have to have a dy dx every time you do it. And this is really the only thing that gives students some trouble. Now, I think everybody's kind of okay with this one, but especially when we did the product rule right here, let's remind us, what it is that we did. The product rule says you take the first function as is, and you multiply by the derivative of the second function. Now, the derivative of y is 1, right? Just like the derivative of x is 1. But then because it was y, you have to then multiply by dy dx. So again, anytime you're taking a derivative of a function that involves y, you have to follow it up with a dy dx. Now, the reason we don't have a dy dx here is because that was the second part of the product rule, which says that you take the derivative of your first term, right? The derivative of x was 1, and then you multiply that by your second term, which was y. So once you get practice doing this, it's not that big of a deal. So now that we have the answer to part A, let's go ahead and try part B. Find the tangent to that curve at the point 3, 3. So we already have the point, we need the slope. The slope, of course, is going to be the derivative dy dx evaluated at the point 3, 3, which means we need to plug x equals 3 and y equals 3 into our derivative. So this will be 2 times 3 minus 3 squared divided by 3 squared minus 2 times 3. And this is 6 minus 9 divided by 9 minus 6, which is negative 3 divided by positive 3, which equals negative 1. And now once we have our slope, we can apply the equation of a line formula, the point slope formula, to get the equation of the line. And when you solve for y, you end up getting y equals negative x plus 6. And that is the equation of our tangent line that you see here. So again, the reason we need implicit differentiation is because if you look at this original formula here, it's not possible, or at least it is extremely difficult to solve for y here. There actually are some formulas for doing this, but it's very, very difficult. Most people don't know the formulas, and in some cases, it will be impossible to solve for y. So this is why we need this new technique of finding derivatives. In the next example, we just want to get a little more practice finding derivatives using implicit differentiation. So this time, notice that you have the sine of x plus y is equal to y squared times the cosine of x. And so it is impossible to solve for y here. So to find y prime, we are just going to take the derivative with respect to x of the left side. and that will be equal to the derivative with respect to x of the right side. Now on the left-hand side, we need to use the chain rule. We have the derivative of sine of something. The derivative of sine of anything is cosine of that thing, and then times the derivative of that thing. Okay, so again, that's just chain rule. On the other side, I want you to notice that we have a product of y squared and cosine of x. So the product rule says we take the first function, y squared, and multiply it by the derivative of cosine of x, which is negative sine of x. Plus, then we are going to take the derivative of y squared and multiply that by cosine of x. So simplifying here, we have the cosine of x plus y times, now the derivative of x plus y is 1 plus dy dx. On the other side, we have negative y squared times the sine of x. So I'm just simplifying this here. And then now we have to take the derivative of y squared, which is 2y times dy dx, times the cosine of x. Now we need to solve for dy dx, but before we do that, it's very important that you see this here. This cosine of x plus y is multiplied to both of these, so you have to distribute that. So we have the cosine of x plus y times 1, which is cosine of x plus y, plus, and then we have the cosine of x plus y times dy dx. And then the right-hand side is the same. Now we need to solve for dy dx. So to do this, we have a term involving dy dx here and a term involving dy dx here. Let's get those on the same side. And so this term and this term that do not have dy dx's also need to be on the same side. So in this case, what I'm going to do is actually take this term here and add it over to the left side. So we will get the cosine of x plus y plus y squared times the sine of x. And then the term that you see here, I'm going to subtract that over to the right-hand side. And so on the right-hand side, we're going to get this term minus this term. All right, so there it is. Now again, why are we doing this? It's pretty much the same reason every time. These two terms that you see here both have a dy dx in them. So we can now factor out that dy dx from each of those terms. And this is what that looks like. And now to solve for dy dx, we just need to divide both sides of the equation by 2y cosine of x minus the cosine of x plus y. And once we do that, these terms will cancel each other out, and we end up with dy dx is equal to the cosine of x plus y plus y squared times the sine of x over 2y cosine of x minus the cosine of x plus y. So one thing that you'll notice right away is that these derivatives are algebraically pretty complicated, and at first they can seem a little bit overwhelming, but once you get practice doing these, you'll find that they're not too bad. And one benefit of doing these problems is that it does give you a lot of practice using algebra. In our final example, let's talk about how to find the second derivative by implicit differentiation. So we'll start the same way. We're going to just take the derivative with respect to x of the left-hand side of the equation, and that needs to be equal to the derivative with respect to x of the right-hand side. Now here we're going to apply this derivative to each one. So the derivative of x to the fourth is 4x cubed, plus the derivative of y to the fourth is 4y cubed, and then times dy dx. And this, of course, is equal to the derivative of 16, which is 0. Solving for dy dx, we are going to subtract 4x cubed from both sides, and then divide both sides by 4y cubed. When we do this, these cancel out, and we end up getting dy dx equals negative x cubed over y cubed after we cancel the 4's here. So this is the first derivative. And of course, we could also write this as y prime equals negative x cubed over y cubed. And let me make a quick comment about using y prime. You'll notice that in all of the examples I've done, when I take a derivative of y, I always write dy dx. I could have written y prime here instead of dy dx. But I like dy dx because when you're looking at a large algebraic expression and you're trying to find all of your dy dx's, they are much easier to find when they are expressed in this way compared to y prime. So that is why I always use this. Now, to do my second derivative, I'm going to write down my first derivative. So dy dx is equal to negative x cubed over y cubed. And to get the second derivative, we need to take the derivative with respect to x of both sides. So d dx of the left side and d dx of the right side. Now when you do this, on the left-hand side, you get d squared y dx squared, which of course is the second derivative. On the right-hand side, when we take this derivative, we need to use the quotient rule. So the quotient rule states you take the bottom function multiplied by the derivative of the top function minus the top function multiplied by the derivative of the bottom function. Now, of course, the derivative of y cubed is 3y squared and then times dy dx. And then you have to divide that by the bottom function squared. So now let's clean this up. So I'm putting the negative 3 in front. And also when I have y cubed times x squared, I usually write that x squared times y cubed. Here I have a positive of 3 x cubed y squared and then times dy dx over y to the 6th. Now, if you're not careful, you might think that you're done here because we have found the second derivative. But we really want this second derivative to be expressed only in terms of x's and y's. In other words, we don't want to have this dy dx in here. So now let's remember that dy dx is negative x cubed over y cubed. And so we can take out dy dx and replace it with this expression. And so when I do that, I'm going to get negative 3x squared y cubed plus 3x cubed y squared times negative x cubed over y cubed, and then all divided by y to the 6th. So now it just becomes an issue of simplifying. And this is where you have to be careful when you have little fractions inside of your big fraction. So let's put a 1 under here. And let's remember that when you multiply fractions like we're doing right here, we can cross cancel. So this y squared is going to cancel out 2 of those y's. And that is going to leave us with negative 3x squared y cubed. And then we have plus 3x cubed times negative x cubed. That's going to be negative 3x to the 6th over y, all over y to the 6th. Okay, so again, I'm just multiplying the tops of these fractions and the bottoms of these fractions. Now, we still have a complex fraction here, so to take care of that, I'm just going to multiply the top and bottom by y. Because doing that will cancel out the y here. Do keep in mind that you have to multiply this to each one. And so this becomes negative 3x squared y to the 4th minus 3x to the 6th divided by y to the 7th. And then from here, in the numerator, we can factor out a negative 3x squared, and we're going to get y to the fourth plus x to the fourth, and in the bottom we have y to the seventh. And this looks like a really good answer. However, remember in the very beginning, your original equation was x to the fourth plus y to the fourth is equal to 16. And in the end, notice that you have x to the fourth plus y to the fourth. So if x to the fourth plus y to the fourth is 16, then I can replace this expression with 16. And so we quite literally get negative 3x squared times 16 divided by y to the seventh. And this is negative 48x squared over y to the seventh. And this is our most simplified second derivative. And that concludes this lesson.